Welcome to the first lecture in this series. Today's topic is green hydrogen. To discuss the fundamentals of green hydrogen, the concept of sustainability has to be addressed. Sustainability in its true sense is usually only achieved if it's based on three pillars, the three E's. Technologies and application must be energetically feasible using efficient conversion. Economic feasibility is the basis for making it work at the private and corporate level. The ecological aspects are probably the easiest to grasp. It is clear that sustainability can only be achieved by protecting the environment. The outcome related to sustainability is the stabilization of climate, weather, and air quality. These factors hugely contribute to the social stability within a region and to the overall prosperity of a society. Hydrogen, especially green hydrogen, will play an important role in the transition to a more sustainable future, improving the lives of humans by stabilizing their natural environment and economic infrastructure. In order to gain an insight into the need for a future sustainable energy carrier, the various primary energy sources available must be discussed. Fossil energy is the most conventional way of storing energy and utilizing it as a fuel for industry and transport. As we will see later, the emission of carbon dioxide poses the greatest drawbacks for this kind of energy source. Also, the ecological issues related to oil and gas extraction clearly show the lack of sustainability. Nuclear energy is heavily burdened by the associated damage that fission material does to the most forms of life. This begins with the mining of uranium and continues through the treatment and storage of waste. To this day, there are no final repositories for highly radioactive waste. Renewable energy is usually available in a decentralized and widespread manner. Direct electricity can be generated from photovoltaics or turbines, usually either wind or water powered. Geothermal energy is also considered a renewable energy source. Chemical energy carriers can be produced by using these energy sources or by processing biomass. These carriers are used for transport and storage. As societies are driven by their respective demand for energy, large quantities of energy carriers are converted worldwide. The annual consumption of fossil fuels is approximately 32 billion barrels crude oil, 3.8 trillion cubic meters natural gas, and 6 trillion tons of hard coal. This equates to 6,750 kilowatt-hours of oil, 4,900 kilowatt-hours of natural gas, and 5,330 kilowatt-hours of coal per person on the planet, indicating a continuous fossil heating output of approximately 2 kilowatt per person. This further results in carbon dioxide emissions of 4,350 kilograms per person and year, based on the consumption of fossil fuels. The statistical review of world energy indicates the proportions of the various energy carriers utilized worldwide. The proportions of renewable hydropower and other renewables, like photovoltaics and wind energy, is only about 13% of the total energy production. One of the most intensely debated sustainability issues is the impact of global warming and the associated influence on life on the planet. Global warming is directly connected to the emission of carbon-containing gases. The most widely discussed one is carbon dioxide. In the atmosphere, CO2 interacts with the cosmic infrared radiation, leading to global warming. For most of the time, the natural carbon cycle has maintained a constant concentration of CO2 in the atmosphere. The chemical conversion of biomass, mainly the digestion of organisms, but also the utilization as a fuel, releases carbon dioxide. Other natural phenomena consume it. The build-up of new biomass by plant photosynthesis converts CO2 into saccharides and other biogenic molecules. Secondly, the absorption in soil and water, followed by chemical conversion, slowly fixes the CO2. But the utilization of fossil carbon sources, such as natural gas and crude oil, has been releasing CO2 in much larger quantities, especially since the beginning of the industrial age at the end of the 17th century, so that this balance is being lost. By now, we have seen the need for a transition towards renewable energy in industry and infrastructure. This is relevant to reduce greenhouse gas emissions and reduce the ecological pressure. Chemical energy carriers are an important factor for storing and transporting the energy, which usually is obtained in a decentralized way. Hydrogen offers great opportunities in this area. Recently, the term green hydrogen has been coined. By assigning a color label to the energy carrier, the different production paths can be compared and evaluated, facilitating the transition to true sustainability. The labels are gray for fossil hydrocarbons such as oil and gas, brown, sometimes black for coal, blue for steam reforming including carbon capture technologies, turquoise for hydrogen from pyrolysis, and pink or purple for hydrogen produced using nuclear energy. Green is the label associated with hydrogen from renewable energy sources. There are several technologies for producing hydrogen. Electrolysis uses electricity to split water into hydrogen and oxygen. It is a mature but still adaptable technology that produces high purity hydrogen, but competes with other electricity-intensive applications. Thermolysis splits water at high temperature, usually using the heat from nuclear power plants. However, the conversion is quite low. Steam reforming is a chemical reaction to break down lighter hydrocarbons in the presence of steam. This mature technology is widely used and costs are moderate. However, the gaseous products require extensive post-treatment to capture large amounts of carbon monoxide and carbon dioxide. Gasification is similar to reforming, which is typically used for heavier hydrocarbons and solids. Biomass gasification allows renewable hydrogen to be produced, although post-treatment and purification is required. The use of biomass leads to the dilemma of using crops or waste. Biogenic hydrogen production, the use of microorganisms in the production stage, is not widely used. Although the resources are large, the output is low, and the biotechnological effort is considerable. Since hydrogen is produced using primary energy, it is considered an energy carrier that can be used on demand. When used as a fuel, hydrogen has the highest molar energy content. However, because it is a gas at ambient conditions, various operations such as compression or sorption must be carried out to store reasonable quantities of it. The conversion of hydrogen to electrical energy can be achieved using fuel cells, as will be discussed later in the series. This conversion does not release any gases other than water vapor. It is considered to be an emission-free energy conversion. The use of hydrogen to buffer fluctuations in energy production from other sources, such as wind or solar, either by storing excess energy or by converting it to electricity when energy is needed, offers an interesting possibility for larger scale applications. In addition, hydrogen is already used as a base chemical for various industrial applications such as metallurgy, cement and fertilizer production. Its use in the food industry should also not be overlooked. Supplementing and replacing these with green hydrogen offers the opportunity to limit emissions in these large-scale applications as well. In general, hydrogen allows efficient storage and transport of energy on a very large scale in the gigawatt-hour range. Storage and transport will be the subject of a separate video. This overview is just a teaser. Transporting organic energy carriers such as oil and natural gas is far cheaper than any other. This is directly related to the high energy densities of liquids and the ease of use of conventional means of transport. The transport of hydrogen by chemical conversion in the decalene-naphthalene system, a liquid organic hydrogen carrier called LOHC, is in a similar range. This is directly related to the conventional means of transport, usually by ship, as it is an organic liquid, and the more complex and therefore costly hydrogenation and dehydrogenation processes to convert the energy carrier. Although the general perception is that energy is transported via high voltage power lines, this is by far the most expensive way. Direct electrical energy transport is of course a viable technique for short distance transport, where the conversion would outweigh the transport costs, but is not a viable way of transporting energy internationally or even intercontinentally. Hydrogen can be transported by pipeline in a similar way to natural gas. However, the difference in its physical properties requires more infrastructure, for example a larger number of recompression stations. But still, green hydrogen pipelines offer an inexpensive solution for transporting low-emission fuels to distant destinations. Of course, pipelines are not the only way to transport hydrogen around the world. One special lecture will cover this topic in detail. With this outlook, I'd like to conclude on the subject of green hydrogen.